Hello everybody. This here is a new series that I want to start. I just quickly look if my recordings have started. And yes, they started. And my series is about the website learncplus.com. And this website is very good. I stumbled over it when I searched for some graphics APIs, and because you have to learn a good amount of programming language to understand an API, they recommended a website called Learn CPP, C++, and this one is it. And I have to say, this is a very good website to build up your knowledge. Like it says, learncpp.com is a free website devoted to teaching you how to program C++, whether you had any prior programming experience or not. The tutorials on this site will walk you through all the steps to write, compile and debug your C++ programs, all with plenty of examples. Becoming an expert won't happen overnight, but with a little patience you will get there, and learncplus.com will show you the way. And my goal is now to use this website to improve my skills. And my idea is to make these videos here. I just go through all the documents and I'm just talking with you like I would teach you, or just like me learning it and going through all the stuff. And if you want, you can speed up everything, or skip whatever you want, or watch it like you want. And I just record it and put it on YouTube, that you can see the learning process I do and that you can do the same as well. And yes, that's it for the intro. I think we can finally start with it. And I would say we start with the 0.1, the introduction to these tutorials. And now I'm going through and I'm reading all this stuff. If you want, you can use this as a listening book or a podcast or something like that. But I'm going through. Welcome to Learn C++ tutorials. Above all else, these tutorials aim to make C++ easy. Unlike many other sites and books, these tutorials don't assume you have a prior programming experience. We will teach you everything you need to know as you progress, with lots of examples along the way. Whether you're interested in learning C++ as a hobby or professional development, you're in the right place. A testimonial from reader Siam from Trinidad is, "It's crazy how perfect this website explains C++ concepts and teaches programming. I read the book Programming Principles and Practice Using C++ by Brian Strostrup, the creator of C++, and it was rather confusing. This website makes it clear the first time, and they explain everything you need to know. Somehow they know what I don't know and what I need to know. It's almost like my future self went back in the past to teach me what mistakes I will make." And then we have the lesson structure. The lessons in this introductory chapter are aimed at giving you some content around what C++ is, how it came about, how programs work, and what software you need to install to create your programs. You will even write your own first program. Further chapters will explore different parts of C++ language. In the first chapter, chapter 1, you will get a broad but shallow overview of many fundamental C++ concepts, so we can start writing some simple programs. Further chapters will explore those concepts in depth. I can't speak this word. Or introduce new concepts. Depth. Each chapter has a theme with all of the sections underneath it's being generally related to that theme. There is no suggested amount of time that you should spend with each lesson or chapter. Progress through the material at a pace that is comfortable for you. Progress through the material at a pace that is comfortable for you. And the goals. Before we get started, let's cover a few important goals for these tutorials. Cover programming topics as well as C++. Traditional textbooks do a pretty good job of teaching the basics of given programming language, but they often do not cover relevant programming topics that are incidental to the language. For example, books will omit sections on programming style, common pitfalls, debugging, good bad programming practices, and testing. Consequently, by the time you finish the book, you may understand how to program in a language, but you might also have picked up bad habits that you will come back to bite you later. One of the goals of these tutorials is to make sure that all of these incidental topics are covered along the way, in the section where it naturally makes sense to discuss them. When you finish, you will not only know how to program in C++, you will know how not to program in C++, which is arguably as important. Provide a lot of examples. It provides a lot of examples. Most people learn as much or more from following the examples as they do from reading the text. These tutorials will endeavor to provide plenty of clear, concise examples to show the application of concepts you are learning. We will also avoid as much as possible the twin evils. The ellipsis, also known as where a necessary or a non-obvious part of an example is omitted in the interest of space, and the unexplained new concept, where a new concept that is integral to the example is introduced without any mention of what it is or how it works. Both of these tend to lead to get stuck. And it provides practice programs. The end of many lessons and sections will contain some exercise that you can attempt to answer on your own. Along with solutions, you can compare your solution against ours to see what we did differently, or if you get stuck, how we solve the problem. Then you can go back and refocus on the areas you need more work on. Most importantly, have fun. Programming can be a lot of fun. And if you're not generally having fun, you're not in the right mindset to be programming. Tired or unhappy programmers make mistakes, and debugging code tends to take much longer than writing it correctly in the first place. Often you can save yourself some time by going to bed, getting a good night's sleep, and coming back to a problem in the morning. Getting the most out of the tutorials. As you go through these tutorials, we recommend a number of practices to maximize your learning experience. Type in the examples by hand and compile them yourself. Do not copy and paste them. This will help you learn where you commonly make errors, as well as becoming familiar with compiler warnings and errors. Don't just transcribe the programs mindlessly. Think about what each of the lines you are typing in does and how it contributes to the overall program. If you encounter anything that you don't understand, that's something to investigate further. As you make mistakes or find bugs in your programs, fix them. Try to solve your own problems before asking others for help. Learning how to find and fix errors is a key skill to successful programming. Don't neglect learning how to use a debugger. We will explain how in the future chapter. It's a key tool in figuring out where your programs are going wrong. And then experiment with the examples. Change numbers and texts to see what happens. Modify the program to do additional things. If a program adds 2 numbers, make it add 3 numbers. Try to find different ways to break the program. If a program asks you to enter a number, try entering a letter instead and see what happens. You will learn more by modifying the examples than by simply following them. Plan to spend some time with the quizzes. If you're new to programming, you may find these challenging. And that's normal, as your brain acclimates to the programming mindset. Don't be discouraged if you don't get the right answer the first time. You may need to try several different approaches before you find the path to success. It's okay to look at the answer if you're really stuck. Just make sure you understand how the provided answer works before proceeding. And then write your own short programs using the concepts you have learned. This will reinforce your learnings and improve your retention. And then common site related questions that are often asked, and how I sign up for the site. There is basically no assignment for this website. And is there a PDF? No, there's also no PDF. It's all on this platform because this platform is free and usable. It is based on ads, and I have to say this out of the content here on this page. It is actually all free and ad based. So if you are searching for the website, you are basically supporting it when you have ads and no ad blocker. Sadly, here I have an ad blocker inside or running because I don't want to put all the ads in this video, or it can also cause some issues for my videos to not have difficulties with the YouTube agreement or rules or guides. And yeah, let's continue with the next question. What should I do if I get stuck on a concept? If you do understand something or feel stuck, read through comments other readers may have encountered similar challenges. And yes, on the bottom here are always comments that you can look up for if you are stuck, and on each example. And scan through the text lessons or 2 in the series. Your questions may be answered there. Yes, exactly there. And use a search engine, for example Google, and ask your questions on a site that is designed for programming Q&A like Stack Overflow. If all fails, skip the material you don't understand and come back later. You may find something that was hard to understand. It's easier with the additional knowledge and concepts provided by other articles. That's basically also why I want to start with this website, because I was a little bit stuck on the place where I was and I want to repeat my basics so I can improve on it. And the next question is, we have 3 more, just short questions. What do I do if I forget what something means? Use the site index, look up any topics you want to know more about there, and you will find links to the lessons. And here we have the site index, and there's basically everything you wish, and you can just search for it and click on it and you will probably find what you are searching for. Even someone that is already knows C++ or is learning, you can use this index and you can search up for it and you have an explanation for it Even if you don't want to use Learn C++, the C++ website, you can still use this index and you will find what you need. And are there any similar sites for other languages? Nope, that would require being able to clone myself a few times. This website by itself, you could go on contact support by yourself if you want to read it. Here we have Alex, he's the builder of this website. He is a bad enough dude on a mission to teach the world C++. And yeah, he has 20 years of experience in desktop applications, CAD, and some more. And if you want to know more about this website, just read the article here if you want. And now we come to the last questions. Can you do a dark mode on its side? Yeah, it's possible, but it's not easy. But you can see darkreader.org, and you can download it. And those is just for the Explorer or for the Google Chrome or Safari, Firefox or Edge, and you can make all dark if you want. And for this one, I think we are through. Here, finally, one small knack. This site is free because it's ad supported. Yes, like I said before, like I mentioned it. If you find yourself enjoying the lessons, please consider disabling your ad blocker. Alright, let's get on with it. And yes, like I said, I have blocked all the ads because I want to make sure I don't have any issues with YouTube and something else, or just to show you the program. Sometimes I put them off just for the website when I use it without making video, but for the video I turn the ads off. And now we can go to the next lesson, 2.0.2, the introduction to programming languages. Modern computers are incredibly fast and getting faster all the time. However, computers also have some significant constraints. They only natively understand a limited set of commands and must be told exactly what they do. A computer program, also commonly called an application, is a set of instructions that the computer can perform in order to perform some tasks. The process of creating a program is called programming. Programmers typically create programs by producing source code, commonly shortened to code, which is a list of commands typed into one or more text files. The collection of physical computer parts that make up a computer and execute programs is called the hardware. When the computer program is loaded into memory and the hardware sequentially executes each instruction, this is called running or executing the program. Machine language. A computer CPU is incapable of speaking C++. The limited set of instructions that a CPU can understand direct is called machine code, or machine language, or an instruction set. Here is a sample machine language instruction: 1011 0000 space 011 00001. Back when computers were first invented, programmers had to write programs directly in machine language, which was very difficult and time-consuming thing to do. How these instructions are organized is beyond the scope of this introduction, but it's interesting to note two things. First, each instruction is composed of a sequence of ones and zeros. Each individual 0 or 1 is called binary digit, or bit for short. The number of bits that make up a single command vary. For example, some CPU process instructions that are always 32 bits long, whereas some other CPUs, such as the x86, x64 family, which you are likely using, have instruction that can be a variable length. Second, each set of binary digits is interpreted by the CPU into a command to do a very specific job, such as compare these two numbers or put this number in that memory location. However, because different CPUs have different instruction sets, instructions that were written for one CPU type could not be used on a CPU that didn't share the same instruction set. That means programs generally weren't portable, usable without major rework, unusable without major rework to different types of system, and had to be written all over again. Because machine language is so hard for humans to read and understand, assembly language was invented. In assembly language, each instruction is identified by short abbreviation rather than a set of bits, and names and other numbers can be used. Here is the same introduction as above as assembly language. Move, M-O-V, all, A-L, and then 061H. This makes assembly much easier to read and write than machine language. However, the CPU cannot understand assembly language directly. Instead, the assembly program must be translated into machine language before it can be executed by the computer. This is done by using a program called an assembler. Programs written in assembly language tend to be very fast. An assembly is still used today when speed is critical. However, assembly still has some downsides. First, assembly language still require a lot of instructions to do even simple tasks. That means a lot of code. While the individual instructions themselves are somewhat human readable. Understanding what an entire program is doing can be challenging. It's a bit like trying to understand a sentence by looking at each letter individually. Second, assembly language still isn't very portable. A program written in assembly for one CPU will likely not work on a hardware that uses a different instruction set and would have to be rewritten or extensively modified. High-level languages. To address the readability and portability concerns, new programming languages such as C, C++, Pascal, and later languages such as Java, JavaScript, and Perl were developed. These languages are called high-level languages, as they are designed to allow the programmer to write programs without having to be as concerned about what kind of computer the program will be run on. Here is the same instruction as above in C, C++ code. A equals 97. Much like assembly programs, programs written in high-level languages must be translated into a format that computers can understand before they can be run. There are two primary ways this is done: compiling and interpreting. A compiler is a program that reads source code and processes a standalone executable program that can then be run once your code has been turned into an executable code. You do not need the compiler to run the program. In the beginning, compilers were primitive and produced slow, unoptimized code. However, over the years, compilers have become very good at producing fast, optimized code, and in some cases can do a better job than humans can in assembly language. Here is a simplified representation of the compiling process. The high-level language source code is compiled by the compiler. Then it produces executable code in the binary code that the computer can read. And then the executable code is run by the hardware and then produces the program that you can see on your display or whatever it does, if it's a sound or something. Since C++ programs are generally compiled well, explore compilers in more detail shortly. We will explore compilers in a more detailed. Since C++ programs are generally compiled, we will explore compilers in more detail shortly. An interpreter is a program that directly executes the instruction in the source code without requiring them to be compiled into an executable first. Interpreters tend to be more flexible than compilers, but are less efficient when running programs because the interpreting process needs to be done every time the program is run. This also means the interpreter is needed every time the program is run. Here is a simplified representation of the interpretation process. We have the high-level language, the code, then it is interpreted. And the interpreter can directly run on the hardware and then process our program. So it basically skips a step that it directly interprets the high-level language source code or high-level language code into a executable code that is directly binary, that can directly communicate with the hardware. And now, optional reading. We also read that. A good comparison of the advantages of compilers versus interpreters can be found here. And if we click on it, we just look at it. Yes, you could difference between compiled and interpreted languages, and then here is a whole article about it. And here are some examples that we have. Neither approach has a clear advantage over the other. If one approach was always better, chances are that we would start using it everywhere. So that says basically you can use a compiler or an interpreter, but they have their own use cases where they are good at, and the compilers are where they are good at. And each one is there where their use case is the best. And that's basically what it says. And you choose if you want an interpreter or a compiler. And now we go further. Most languages can be compiled or interpreted. However, traditionally, languages like C, C++, and Pascal are compiled, whereas scripting languages like Perl and JavaScript tend to be interpreted. Some languages like Java use a mix of the two. So as you can see, like I said, you have the specific languages that prefer other things, like scripting, JavaScript, or we use interpreter for it because it suits it better, and we use the compiler for C or C++ or Pascal because it suits that better. And when we continue, high-level languages have many desirable properties. First, high-level languages are much easier to read and write because the commands are close to natural language that we use every day. So it has basically English words that we understand, so we can understand the language. That's the basis of high-level languages. And then second, high-level languages require fewer instructions to perform the same tasks as lower-level languages, making programs more concise and easier to understand. Yes, it's not like assembly language because you need like 5 more instructions while you write 1 in C++. And that's why you use higher level languages, so you have a smaller code and the same output, and maybe it's also at the same speed when it's running. And in C++ you can do something like a equal b multiplied by 2 plus 5 and in one line. In assembly language this would take 5 or 6 different instructions. Yeah, exactly. Perfect example what I just said. And third, the programs can be compiled or interpreted for many different systems, and you don't have to change the program to run on different CPUs. You just recompile for that CPU. As an example, you have the high-level language. Then this high-level language compiles to x86. Those are assembly languages most of the time, and then we can translate this language to x86 or compiler for PowerPC hardware or compiler for MIPS hardware, and then those languages are then suited for the program that is, or the hardware that uses this language, that then it can, and you can write one code and run it basically everywhere as long you have the compiler to make it executable on the other platform. It has just to be transformed in the way you want. And there are two general exceptions to portability. The first is that many operating systems such as Microsoft Windows contain platform-specific capabilities that you can use in your code. These can make it much easier to write a program for a specific operating system, but at the expense of portability. In these tutorials, we will avoid any platform-specific code. That means, that this code that we write, we can basically run everywhere on every platform that we want, as long we compile it to the right hardware or right assembly to run on the hardware. And the second is that some compilers also support compiler-specific extensions. If you see these, your programs won't be able to be compiled by other compilers that don't support the same extensions without modification. We'll take more about these later once you have installed the compiler. So I will talk later about it because you will understand it much better later. And rules, best practices, and warnings as well. As we proceed through these tutorials, we will highlight many important points under the following 3 categories. The rules are purple. Rules are instructions that you must do, as required by the language. Failure to abide by a rule will generally result in your program not working. So you have to do all the purple things. And then the green one, the best practice. Best practices are things that you should do because that way of doing things is generally considered a standard or highly recommended. That is, either everybody does it that way, and if you do otherwise, you will be doing something people don't expect, or it is superior to the alternatives. And then the warning. Warnings are things that you should not do because they will generally lead to unexpected results. Either confusion in the code so you cannot understand it later, or just codes that will have problems later when you continue, and you better not do that. And yeah, with that we finished our zero point 0.2 instructions to programming languages, and we can continue to instruction to C, C++. Before C++, there was C. The C language was developed in 1972 by Dennis Ritchie at Bell Telephone Laboratories, primarily as a system programming language, a language to write operating systems with. Yes, to write operating systems with. Ritchie's primary goals were to produce a minimalistic language that was easy to compile, allowed efficient access to memory, produced efficient code, and was self-contained, not reliant on other programs. For a high-level language, it was designed to give the programmer a lot of control while still encouraging platform, hardware and operating system independence. That is, the code didn't have to be rewritten for each platform. C ended up being so efficient and flexible that in 1973 Ritchie and Ken Thompson rewrote most of the Unix operating system using C. Many previous operating systems had been written in assembly. Unlike assembly, which produces programs that can only run on specific CPUs, C has excellent portability, allowing Unix to be easily recompiled on many different types of computers, and speeding its adoption. C and Unix had their fortunes tied together, and C's popularity was in part tied to the success of Unix and an operating system. Unix as an operating system. In 1978, Brian Kernighan and Dennis Ritchie published a book called The C Programming Language. This book, which was commonly known as Key and R after the authors of last names, provided an informal specification for the language and became the de facto standard when maximum portability was needed. Programmers would stick to the recommendation in Key and R because most compilers at the time were implemented to Key and R standards. So yeah, if we are interested in the C language, I think this book would not be a bad choice to just one-time purchase and look into it. And in 1983, the American National Standard Institute (NSI) formed a committee to establish a formal standard for C. In 1989, committees take forever to do anything. They finished and released the C89 standard, more commonly known as ENSI-C. In 1990, the International Organization for Standardization, ISO, adopted ANSI-C with a few minor modifications. This version of C became known as C90. Compilers eventually became ANSI-C C90 compliant, and programs desiring maximum portability were coded to do this standard. In 1999, the ISO committee released a new version of C called C99. C99 adopted many features which had already made their way into compilers as extensions or had been implemented in C++. C++. C++, pronounced C++, was developed by Brian Strastrup at Bell Labs as an extension to C, starting in 1979. C++ adds many new features to the C language and is perhaps best thought of a superset of C. Though this is not strictly true, as C99 introduced a few features that do not exist in C++. C++'s claim to fame results primarily from the fact that it is an object-oriented language. As for what object is and how it differs from traditional programming methods, well, we will cover that in a later chapter. C++ was standardized in 1998 by the ISO committee. This means the ISO Standard Committee approved a document describing the C++ language to help ensure all compilers adhere to the same set of standards. A minor update to the language was released in 2003 called C++03. 5 major updates to the C++ language, C++11, 14, 17, 20 and 23 have been made since then, each adding additional functionality. C++11 is particularly added a huge number of new capabilities and is widely considered to be the new baseline version of the language. Future updates to the language are expected every 3 or so years. Each new formal release of the language is called a language standard or language specification. Standards are named after the year they are released in. For example, there is no C15, C++15, because there was no new standard in 2015. C and C++'s philosophy. The underlying design philosophy of C and C++ can be summed up as trust the programmer, which is both wonderful and dangerous. C++ is designed to allow the programmer a high degree of freedom to do what they want. However, this also means the language often won't stop you from doing things that don't make sense, because it will assume you're doing so for some reason doesn't understand. Because it will assume you're doing so for some reason it does not understand. There are quite a few pitfalls that new programmers are likely to fall into if caught unaware. This is one of the primary reasons why knowing what you shouldn't do in C++ is almost as important as knowing what you should do. And then to the questions in this chapter. What is C++ good at? C++ excels in situations where high performance and precise control over memory and other resources is needed. Here are a few common types of applications that most likely would be written in C++. Video games, real-time systems for transportation, manufacturing, high-performance financial applications, high-frequency trading, graphical applications and simulations, productivity, office applications, embedded software, audio and video processing, artificial intelligence and neural networks. And there are also many more that you can list here that needs some performance, or C++ is good for the memory management. And then to the next question, we have, do I need to know C before I do these tutorials? And definitely nope. It's perfectly fine to start with C++. And and we will teach you everything you need to know, including pitfalls to avoid along the way. Once you know C++, it shouldn't be pretty easy to learn standard C. It should be pretty easy to learn standard C if you ever have the need. These days, C is mostly used for niche use cases, code that runs on embedded devices when you need to interact with other languages that can only interface with C, etc. For most other cases, C++ is recommended. And with that, we have our chapter 0.3 Introduction to C++, and we can go to the next one, 0.4 Introduction to C++ Development. Before we can write and execute our first C++ program, we need to understand in more detail how C++ programs get developed. Here is a graphic outlining a symbolistic approach. Step 1. Define the problem to solve. For example, you need an application that's, for example, a calculator that can add your numbers that you have on a certain list. And then you make a program for that. And then you have to design how you want to do that for step 2. And then step 3. Write the program that implements the solution so that it adds all the numbers. And then, after you have written the program, compile the program, so for testing if all works. Then link objects files, and we will know more about that in step 5 because I cannot explain it right now. And then step 6, test the program if it suits everything that you want, and otherwise debug it and return to step 4, step 5 and 6. And now we go through in detail through all the steps. Define the program that you would like to solve. This is the what step, where you figure out what problem you are intending to solve. Coming up with the initial idea for what you would like to program can be the easiest step or the hardest. But conceptually, it is the simplest. All you need is an idea that can be well defined, and you're ready for the next step. Here are a few examples. I want to write a program that will allow me to enter many numbers, then calculates the average. It's basically exactly what I said for the example. I haven't read the article before. And I want to write a program that generates a 2D maze and lets the user navigate through it. The user wins if they reach the end. I want to write a program that reads in a file of stock prices and predicts whether the stock will go up or down. And this is step 1. Now to step 2. Determine how you are going to solve the problem. This is the how step, where you determine how you are going to solve the problem. You came up with step 1. It is also the step that you most neglected in software development. The crux of the issue is that there are many ways to solve the problem. However, some of those solutions are good and some of them are bad. Too often a programmer will get an idea, sit down, and immediately start coding a solution. This often generates a solution that falls into the bad category. Typically, good solutions have the following characteristics. They are straightforward, not overly complicated or confusing. They are well documented, especially around and assumptions being made or limitations. They are built modularly, so parts can be reused or changed later without impacting other parts of the program. And then fourth, they are robust and can cover or give useful error messages when something unexpected happens. When you sit down and start coding right away, you're typically thinking, I want to do something. So you implement a solution that gets you there the fastest. This can lead to programs that are fragile, hard to change and extend later, or have lots of bugs, technical defects. As an aside, the term bug was first used by Thomas Edison back in the 1870s. However, the term was popularized in the 1940s when engineers found actual moth stuck in the hardware of an early computer, causing a short circuit. Both the log book and in which the error was reported and the moth are now part of the Smithsonian Museum of American History. It can be viewed here if you want. Studies have shown that only 20% of programmers' time is actually spent Studies have shown that only 20% of a programmer's time is actually spent writing the initial program. The other 80% is spent on maintenance, which can consist of debugging, removing bugs, update the code with changes in the environment to run on a new OS operating system version, enhancements, minor changes to improve usability or capability, or internal improvements to increase reliability or maintainability. As an aside again, this is a great illustration of the Pareto principle. Consequently, it is worth your time to spend a little extra time up front before you start coding, thinking about the best way to tackle a problem, what assumption you are making, and how you might plan for the future in order to save yourself a lot of time and trouble down the road. We will talk more about how effectively design solutions to problems in the future lessons. Step 3. Write the program. In order to write the program, we need two things. First, we need knowledge of a programming language. That's what these tutorials are for. Second, we need a text editor to write and save our written programs. The programs we write using C++ instructions are called source code, often shortened to just code. It's possible to write a program using any text editor you want, even something as simple as Windows, Notepad, or Unix VI or Pico. A program typed into basic text editor would look something like this. We have the include, IOStream, int main, sd count, here is some text, and then return to 0. We will look at that later, what this does. And now, however, we strongly urge you to use an editor that is designed for programming, called a code editor. Don't worry if you don't have one yet, we will cover how to install a code editor shortly. A typical editor designed for coding has a few features that make programming much easier, including line numbering. Line numbering is useful when the compiler gives us an error, as a typical compiler error will state some error code message line 64 without an editor that shows line number without an editor that shows line numbers. Finding line 64 can be a real hassle, because in just an editor there is no error notification that says yes, it's on line 64. It just says it does not work. And for this, if you have an editor that can figure out where it is, it's very useful. Then 2. The syntax highlighting and coloring. Syntax highlighting and coloring changes the color of various parts of your program to make it easier to identify the different components of your program. Yeah, if you have a function, if you have just a normal command or a class, they have every time a new color, and it makes it much easier to figure out what is. And then third, an unambitious fixed width font, often called monospace font. Non-programming fonts often make it hard to distinguish between number 0 and the letter O, or between the number 1, the letter I, lowercase l, and the letter I, uppercase I. A good programming font will ensure these symbols are visually differentiated. For example, you have a 0 with a line in between, or a circle, in order to ensure one isn't accidentally used in place of the other. All code editors should have this enabled by default, but standard text editor might not. Using a fixed width font where all symbols have the same width makes it easier to properly format and align your code. Here's an example of a C++ program with line numbering syntax highlighting a fixed width font. This word. And here we have the same again, and you can see up here we have just the editor, and for the example on return to 0, you can see the 0 is basically like a O, and you cannot make a big difference. And here you have all the colors for the function, for the library IO stream, for the text that you want to insert. Here is some text, and return 0 has a line in it, and you can see it much better than just in the text editor. And then note how much easier this is to understand than the non-highlighted version. The source code we show in this tutorial will have both line numbering and syntax highlighting to make that code easier to follow. And then we have a tip. Coding Font has a neat tool to allow you to compare different coding fonts to see which ones you like best. So you can change them in your API, in your coding platform for example ADI. This is for example Visual Studios. You can change how you want to mark these. You can basically make this red text here orange, or return. You can change that if you want, or just make a new layout from the different coding fonts that are available on the ADI. And then we come to, for advanced readers, maybe you are one of them, because source code is written using ASC2 characters. Programming languages use a certain amount of ASC2 art to represent mathematical concepts. For example, equal with a line through it is not part of the ASC2 character set, so programming languages typically use an exclamation mark equal to represent mathematical inequality instead. Some programming fonts such as Fira code uses ligature to combine such art back into a single character. For example, instead of disabling exclamation mark equal, Firma code will display the equal to with a line through it, using the same width as the two-character version. Some people find this easier to read, others prefer sticking with a more literal interpretation of the underlying characters. The programs you write will typically be named something .cpp, normally just a .cpp, it's a CPP file, where something is replaced with the name of your choosing for the program. For example, calculator, high, low, or some more like hello world or whatever. The CPP file extension tells the compiler and you that this is a C++ source code, C++ code source file that contains C++ instructions. Note that some people used extension .cc or .cxx instead of .cpp, but we recommend you use .cpp. Best practice: name your code files something.cpp, where something is a name of your choosing, and .cpp is the extension that indicates the file is a CPP C++ source file. Also note that many complex C++ programs have multiple C++ files, although most of the programs you will be creating initially will only have a single CPP file. It is possible to write single programs that have tens or hundreds of CPP files. Once we have written our program, the next step are to convert the source code into something that you can run and then see whether it works well. We will discuss those steps 4 to 7 in the next lesson. And this will do it for the episode today. In the next episode you will see the step 4 to 7 and some more, and we can even go back to the table content, to the home. We can even scroll out a little bit so you can see no, I'm still in here. You can see how many chapters we have here. We are here in the 4th chapter, but there are many more we can go through. This will have, or we will have a lot of videos with that, multiple hours long, probably for a long time, and we will go through most of them because I want to learn C++, and if you want to see more, keep watching those videos. And beside this content I do here, I will also put other videos up because I have a calculator project running at the moment and another book that I was working on, but because of lacking knowledge of in the current state, I went here because I had a good feeling about it, that I learn with this, and then I can go back to my book. If you want to know, it is Beginning C++ through Game Programming. I was in the chapters with classes and object-oriented programming, and as you can see here, object-oriented programming will come way down here. References, classes. Here, they will start in chapter 14, and we have a long way until chapter 14. And that's what we do on this channel. If you're interested in watching some more videos, feel free to stay on my channel, leave an abo, and I'm happy if you're here. And I would say either you had some fun watching it or learned something watching it. And with that, I say bye.